Hey guys, welcome back. This is episode 2 of quantum chemistry lectures. So we're ready to tackle these atomic orbitals. Just made myself a tea, recovered my voice, and my voice sounds super annoying when I hear it. So in my head somehow it sounds better, but when I heard it, when I rewatched my first lecture, video recorded. Man, I sound terrible. So hopefully you're not too irritated by my voice. So let's just focus on the content, okay? The message is what's important, not the messenger. All right. So, so we're gonna go over these atomic orbitals, and we have a couple of interesting concepts coming up. So I'll be using my notes, but I'll be going back and forth between the website and my Notability a Notability app. So let's shift to there. Okay, so we're introducing a hugely important concept for chemistry, the concept of atomic orbitals, and essentially it's the wave function of one electron systems. Okay, so that's it. So orbital is the same thing as the psi wave function that we wrote in the last lecture, if you watched, if you're present on Friday lecture, right? So we're gonna call these guys orbitals. And notice that orbitals, while sound similar to orbits, they have nothing in common. Okay, orbit was just a classical mechanics idea, the way planets orbit around the sun, right? And that's the model that Bohr developed, but it was wrong. So orbitals refer to wave functions. So orbitals, while replace the orbits, right, they're totally different objects. So it's an abstract mathematical wave function that gives you the probabilities to find the electron. All right, so we're going to talk a lot about orbitals in atoms and molecules. For the hydrogen atom, it's nothing but the wave function we just looked at in the last lecture. Okay, in this lecture, we're going to closely examine their shapes, their nodes, quantify how many nodes each orbital has, and then show how this number of nodes related to different quantum numbers. We're going to look into nodes that come from the radial part, nodes that come from the spherical part, and the total number of nodes. Okay, so let's start with the radial part, right? And notice that we're gonna have a radial wave function here squared, because we're squaring the wave function, right? That depends on the radial and spherical part, right? The radial part, the spherical part. And notice that there is this little guy present, the r square. Where did it come from, right? So as I explained in today's lecture, when you're working in spherical coordinate systems, you gotta make sure you carry over the volume element. Okay, so when we're working with Cartesian coordinate system, right, we're just simply squaring the wave function and calling it the probability distribution. Okay, because that's what appears in front of the volume element, the differential element dx. But when you're working with spherical coordinate system, your volume element's going to look a little different. Okay, so it's going to look dx, dy, dz. So you just have to square the wave function and that's it. But if you're working in spherical coordinate system, you're going to have this extra factor that must be carried over. Okay, and we're talking about this guy, r squared sine theta. And since we're looking only at the radial part, we're going to focus on this factor. So we must carry the r square. Okay, and if you integrate over the angles, right, which is what happens if you want to reduce your variables down to r, right, you integrate them from 0 to pi for the theta and 0 to 2 pi for the phi, you're gonna end up with 4 pi. Okay, so that's what gives you the volume of the sphere, that 4 pi r cubed divided by 3. All right, so this is important mathematical nuance, right, that we must carry over this volume element, right, this term in front of the differentials dr, d theta, dphi. And let's see what's the impact of it, right? If we were to simply square the wave function of the 1s electron, right, which looks like an exponential, a decaying exponential, right, then we would get an unphysical result that the most likely position to find the electron is right in the middle of the nucleus. that doesn't make sense, right? The whole atom would explode, the universe would collapse, and I won't want to be here speaking to you. So clearly that's not true. Now, if we account for the this volume element, which you see that grows with R, and the wave function decays with R, you multiply these two guys together, then you get the correct answer that the most likely position to find the electron is somewhere in between, infinity and right at the center of the nucleus. And here you see the histogram. You can think of it as experimental data, right? You did experiments. You find sometimes electron here, other times there, other times there, other times there. You histogram your result, and the curve shows you the wave function square with the volume factor, and you see that the experiment and theory match very nicely. Okay, in fact, the theory is even better because it gives you a nice, smooth, continuous curve, while the histogram depends on how many experiments you did. Okay, and here is the three-dimensional visualization of the same thing. You can see that there's a whole bunch of black dots, right? So this could be a result of a single experiment. You're hitting the electron with a photon, and you're finding it here, there, everywhere, right? And you're putting a dot, and you find that there is most likely to find the electron is somewhere in this concentric sphere, right, closer to the nucleus, and the probability tends to kind of decay as you move out. Okay, and this is kind of the three-dimensional visualization of the same result. Okay, so we see a dramatic departure from the Bohr model. We see that the electron behaves probabilistically, and the only information that we can extract is the probability to find it in different locations in space, and that probability is given by taking the wave function, squaring it, and not forgetting that if we're in a spherical coordinate system, we must carry over the factor that comes out of the volume element. Okay, so Cartesian coordinate system, there is nothing to worry about, but for spherical, cylindrical, and other coordinate systems, you get some volume elements, and you must not discard those. Okay, that's not how mathematics works. All right, so that's very nice, and this distance, the most likely distance to find the electron, right, is called the Bohr radius, called A0, that we use to to turn the wave functions into some nice dimensionless forms. All right, so that's very nice, and that was a result for 1s. You can begin to appreciate the consequence of nodal points when you start plotting 1s, 2s, 3s orbitals, right? So these are wave functions that correspond to value L0. We'll see that when L is not equal 0, the shapes are going to get more funny, more interesting, more exotic. But when L is equal 0, all you have is spheres. But some of these spheres would have basically holes, right? They're going to be places where electron is never to be found. And that's kind of crazy. Like, why would electron try to avoid certain locations? And the answer is quantum mechanics. It predicts wave functions. Wave functions behave like waves with a constructive, destructive interference patterns, right? So they're kind of like standing waves that we've seen in particle in a box, right? And they'll have some locations where the electron is never to be found. Okay, so you can also say that this is a quantization of position of the electron. Okay, so 1s electron has no nodes, so it sort of has nice clump of points. But as you go to 2s, you see that there is a nodal surface, basically area where electron completely avoids. Probability is equal to 0. And you go to 3s, you see that there is 2 layers. Okay, so this is very interesting. It looks like the electrons are existing as like these probabilistic waves, as like these sitting probabilistic waves, and this sort of gave rise to the concepts of electronic shells, because they're like structured in this kind of layers. So it's really fascinating. And here's the kind of a theoretical prediction of this, shown as field spheres. So it's like a nested spheres of probability. Okay, and these nodes and shapes of these orbitals have huge implications for chemistry, and you can predict a lot of interesting properties, ionization energies, the binding energies. So here we're visualizing 1D radial part of the wave function square, right? Notice again that we have the the R factor in there. So 1s orbital, right, or 1s wave function describes the electron that can be the closest to the nucleus, right? And as we go to n equal 2, n equal 3, you see that the probability is shifting to higher and higher values. So that's one feature to notice, and that makes sense, right? Because you're exciting the electron, and eventually you're going to kick it out when you supply enough energy. It's going to be, the atom is going to be ionized, so the electron is going to fly away. So we do expect the electron to be pushed further and further as we excite it to higher quantum levels. Okay, so what's the other feature to notice here? And oops, I dropped my iPad pen. I'm gonna grab it. So the other feature you notice is that you have these nodal points and you have some local peaks for every single orbital. Okay, so it just shows that 2s has some finite, non-negligible probability to be in the territory of 1s. And the same way with 3s, right? It has some finite, non-negligible probability to sort of penetrate into the territory of 2s. Okay, so electrons do act in these ways. Okay, so they can also be in regions which are largely dominated by other orbitals, and this has consequences, right? They could shield the charge of the nucleus, and they can lead to weaker sort of bound states for the outer shell electrons. So in particular for the s orbitals, this has important consequences for electronic structure. So those are some features that we learned by examining the shapes of the orbitals. Okay, so the average distance of the electron away from the nucleus. So this is an expression that we looked at the end of the last lecture, right? So here's a quantitative expression that you see how this thing grows with the quantum number and how it depends on L, right? So you can plug in the values of L and N, and you can do some computation. And I think in some of your problems this is what's asked. All right, so this is the motivation for why we need to study the shapes of the orbitals on the example of 1s orbitals, but we have much more fun shapes when we look at the orbitals that are characterized by different values of L quantum number, the orbital quantum number, right? And here are the shapes of those guys, right, where L is not equal to 0. In particular, you see that here, and here, right? L is equal 1, and ML, the projection of L, ML quantum number goes from -0, 0, and 1, and you see the different fun shapes that result, and you have the result for L2 here and L3. So basically, you see that orbitals that are characterized by non-zero L, they have non-spherical shapes. And these orbitals lead to very interesting bonding patterns in elements that have in multi-electron atoms that have d orbitals, p orbitals, f orbitals. So this directionality of the wave function is going to lead to different types of bonding and structure of molecules. Okay, that's why we chemists, chemical engineers, biochemists, even physicists care a lot about characterizing these orbital shapes. And these are the orbital shapes that we'll be carrying with us to describe the other atoms and molecules. Now notice here that some of the shapes look a little different from what you might have expected based on your general chemistry courses. In particular, 2p-1 and 2p1 looks like a donut. Maybe you're expecting something else. So let me explain where these visualizations come from. Okay, so the wave functions, right, of the hydrogen atom, they have complex numbers in them, right? So there's different ways of visualizing. So one particular way that chemists have chosen to visualize, right, is to take a linear combinations to degenerate orbitals and form an orbital that's a purely real function. Okay, so here you see how px results by taking a combination of p plus 1 minus 1, and how py results from a linear combination with some complex number thrown in there. So essentially, what chemists have done, and let me show you the animation here, they have converted these wave functions into real form that correspond to exactly the same probability and exactly the same energy, but they allow visualization, a better visualization. Okay, so here you're showing the animation of this. You see how by taking a linear combination of P1 and P minus 1, right, you can end up with a purely real function that you can visualize. And the visual image is that of a familiar dumbbell or two lobes, whatever you want to call the p shape, p orbital shape, familiar from chemistry literature. And here are the shapes of 2px, 2py, 2pz. So I guess the important thing here is to know what chemists have done, right? So they've simply chosen a convenient way of visualizing this orbital. They haven't changed them in any way. They just, use the fact that these are degenerate orbitals. You can take a different linear combination and find a convenient one that turns the function to purely real form. And if you have a real function, you can just throw your favorite 3D visualization and get these beautiful shapes. Okay, so this is what chemists use. Physicists, though, they're not. They're often, okay with just sticking with these donut shapes. Okay, so it's just a preference. Chemists versus physicists, they usually have different tastes when it comes to certain things. All right. So here is another beautiful visualization of the orbitals showing you the probability density with light color indicating the high probability and dark color indicating low probability with black indicating essentially zero probability. Okay, so this is as if you shine light on the electron and see where it's most likely to be found. And you see the directionality of different orbitals, right? You see the spherical orbitals characterized by values of L equals 0, non-spherical orbitals characterized by non-zero values of L. You have the P, you have the D orbitals, you have the F orbitals. So they give you these beautiful shapes, and you can reconstruct them by taking linear combination of degenerate P, D, and F orbitals. Okay, and this is the full periodic table, I guess you can say, of the orbitals that shows you the different fun shapes of S, P, D, and F orbitals. Notice that in this plot we're also highlighting the sort of nodal lines that emerge from going to higher and higher quantum numbers. Right, it becomes kind of difficult to visualize. Right, you see that you add a nodal lines when you increase the n for the s orbital. It turns into concentric spheres. And if you look at the p orbitals, they become sort of concentric dumbbells, funny mushroom shapes, whatever you want to call it. And for the d and f orbitals, it becomes even more crazy looking, but the pattern is familiar, right? So you increase the quantum number, you add another nodal line. Okay, so that's something we've seen. It's just that these orbitals have really complex spatial shapes. All right, so here's some more animated plot of the orbitals that you can visualize. It's showing you the s orbital. You can turn to different orbitals to visualize 3 pi y. So you basically see the extra nodal lines. If I go to, let's say, 2 pi y, there could be one less. Okay, so and here you're seeing the clouds scatter plot visualization. You can think of each point as being a single experiment. You hit the electron with a photon, you find it somewhere, and the places where you have high concentration of points means this is the more likely place to find the electron. You see for the p orbital, you have this nodal plane where the electron is never to be found. Okay, and you can explore different kinds of orbitals. Let's take a look at these ones. Really beautiful. The color here indicates the sign of the wave function, positive to negative, but for the probability, that it's the square of the wave function matters. So sign would be important. for molecular bonding later on, but for probability distribution doesn't make a difference. Let's also check out, let's see if they have the complex visualizations, right? The donut looking shapes that I just showed. Yeah, so here we're gonna get, oh no, it's actually showing all the same. I was looking for donut shape. Anyway, so you can explore the orbitals, but in a more sort of animated setting. All right, let's see, how do I get out of this? So what are our objectives here, right? So our objective here is to predict the shapes of the orbitals and their nodal lines and nodal surfaces. And here I have some problems and solutions for you guys, so I encourage you to go over it. Some of them have full solutions, others have hints or partial solutions. So for instance, the problem 1 is asking you, how many possible quantum states you can have when n is equal to 3, and listing degeneracies. So we know that there's a degeneracy with respect to L and ML, and you can list them explicitly. L is equal 0, M is equal 0, L is equal 1, M runs over all the projections, minus 1, 0, 1, L is equal 2 will be minus 2, minus 1, 0, 1, 2, and you can count the number of wave functions, right, that corresponds to these quantum numbers. And here you have 1, 3, and 5. Okay, you sum up together, it's going to give you 9. So indeed, you have n square degeneracy. Okay, this is when we ignore the spin. If there's spin, it would be 2 times n squared. But in the absence of spin, you can just take n and square, and it will give you exactly the degeneracy number of degenerate states. Okay, and this is showing you the energy of the electron. And you have some other problems about the values of the angular momentum. So this is again something that we've seen in the rigid rotor problem. And here, you can also solve them here, right? So the ML takes the values from minus L all the way to plus L, and the last one is asking about the orientation. This is basically a vector object. It's L divided by L cosine theta. It's kind of a unimportant problem, this one. All right, so problem 3 is more interesting, right? It's asking you to locate the nodes. Okay, so we know that there are places where the electron is never to be found, and you can see it by looking at the wave function, identifying which part is going to make this wave function 0. Okay, and you can look at the spherical part. There's a cosine, so cosine becomes 0 when theta is equal to pi half. And for the r part, we have some polynomial. We can set this thing to 0 and then see what values the r returns. And if you do that, you're going to see r equals 0 and r is equal to 6a0, the Bohr radius. And those are the values where the wave function becomes 0. Okay, and besides these shapes and nodes kinds of questions, which are relatively straightforward, there's just basically a couple sort of simple expressions to know, and this will also be available to you. The total number of nodes is n minus 1. Angular nodes contributes L, and the angular nodes would be n minus 1, n minus L minus, or the radial node, sorry, it will be n minus 1 minus L. So those are relatively straightforward to solve. Okay, so other kinds of problems with this hydrogen atom chapter is calculating various, average, maximum probability positions of the electron. All right, the problem 4 is that type. So you have the explicit solution. So I encourage you to go over it and see how everything works out. So this is, a problem that maybe, mathematically takes a couple more steps to solve, but conceptually is very similar to the particle in a box that we did. So you're given a wave function, and you're asked to calculate the average distance. Okay, so you throw this into the sandwich expression, right? And here the challenge is that you have to take care of all these variables of phi, theta, r, not forgetting the volume element and the integration limits. So please study this expression, make sure that every part makes sense. Okay, so if you take care of all these variables and the integration limits, you end up with an integral that's relatively easy to evaluate, and there's a table integral that's given to you, and you can compute, and you get this expression of 3/2 a0. Or you can use that generalized expression that we've shown in the first lecture, right? The average position of the electron given any orbital by NL values. Okay, so you can calculate that. Now, just like in particle in a box problem, right? We emphasize the difference between the average distance, the probability to find the electron in some location, and probability to find in some region, as well as the most likely point to find the electron. And this can be obtained by using different operations with a wave function. Okay, so to find the probability in some range, you have to carry out the integral within that range. Let's say you're interested in the probability to find the electron and within the first peak or the first Bohr radius, you can do the integral from 0 to a0. Okay, so that's kind of the expression to use. And if you want to find the most probable value, then you have to take the derivative with respect to r and then set it to 0, and by solving it you'll find the r maximum. So those are the typical calculations that we've done with wave functions, and the only difference here is that, well, we have 3 more variables to worry about, and we have the volume element with this factor of r squared sinus theta. But if we can get over this fact, then at least we can write down the expression. So I won't be torturing you guys with complicated integrals, maybe just a couple simple ones in your homework. And if there is anything in the exam, it's going to be super simple. Maybe most of the time just asking you to write down the expression and not do anything with it. Okay, because our job here is to learn the higher level concepts and not do lower level math. All right, and then the final type of problems to mention here are the problems of saying whether the one eigenfunction would be orthogonal to the other, or is it normalized, is it not normalized. So for this I'm referring you guys to the book. There's nothing remarkable about them. They're very similar to particle in a box, the difference being that these are hydrogen atom wave functions. Okay, so this concludes the topic of atomic orbitals of the hydrogen atom. A really important concept has emerged from here that we'll be carrying with us to multi-electron atoms and multi-electron molecules. So please make sure to play with these shapes, study different orbitals, appreciate their nodal lines and surfaces that emerge. All these shapes will be used as building block to create beautiful molecular orbitals in different organic and inorganic molecules. Okay guys, thanks, and times for my third cup of tea.